Hey guys, welcome to another short lesson. So in today's video, I'm going to introduce the idea that a random variable, let's call it x, has two components. One is called the fixed component and the other is called the random component. So in order to understand the difference between the fixed and the random components, let's begin with a very simple example because that's going to make things easier for us to understand. So let's say that x is defined to be the value that comes up when we throw a die. So using that information, we can fill up the first column. And if you don't understand why I'm doing what I'm doing, you can watch my other video where I explain in more detail how you can fill up this table. So basically in the first column, we have just filled in the values, the possible values that x can take. And we know that when we throw a die, these are the possible values that x can take, right? So that's pretty straightforward. The next thing that I'm going to do is to note down the probability with which each of these values can come up. So we know that the total number of possible outcomes is 6, right? So the denominator is going to be 6, and we know that assuming that it's a fair die, the probabilities with which each of these values can come up is going to be equal, right? So each of these values are equally likely to show up. So the probabilities associated with each of these values is going to be the same. That is 1 over 6. Okay, cool. So far, so good. The third column is simply going to represent the weighted values where I'm going to multiply the values in the first column with the values in the third column. So once again, this can be filled up very quickly. So 1 into 1 over 6 is 1 over 6, 2 into 1 over 6 is 2 over 6, and so on and so forth. So this can be filled up quite easily. Cool. Okay, the next thing that we need to do is, in order to obtain the expected value of x, that is the population mean of x, we need to sum up all of these values in the third column, and this is something we've done before. So this is going to equal 6 plus 5 is 11 plus 4 15 plus 3 18 plus 2 20 21 over 6. So the sum is 21 over 6, and that means that our population mean, that the population mean of x is equal to 21 over 6, which is equal to 3.5. Okay, cool. So what we've done here is simply calculate the population mean of x using the idea that the random variable x is defined to be the value that comes up when we throw a single die. Okay, so the first thing that you need to notice is the fact that 3.5 is a value that x never actually takes in practice. So x can either be 1, or it can be 2, or it can be 3, 4, 5, or 6, but it never actually takes on the value 3.5, right? Obviously. So this is the first thing. Now, moving on. So the reason that we introduced that example is to understand the idea that the actual value of x in any given observation is going to be different from the population mean, that is mu x. So let's say that we have xi, which is the actual observation that we get. Xi is going to be equal to mu x, which is the population mean. And this is going to be fixed for all observations. It's going to be the same every time, plus a random component which is denoted by u. So this is going to be different for every observation. So we have decomposed xi into its fixed and random components. So let's say when we throw the die, we get a 5. And we know that mu is always equal to 3.5. So ui in this particular instance is going to equal 1.5. So basically, we're trying to decompose xi, that is our observation in any given throw, is going to equal a fixed component and a random component. And this random component, the difference between xi and mu x, is denoted as ui. So in this video, I have only introduced the difference between the fixed and the random components. And using these ideas, In the next video, I'm going to prove that the expected value of ui, that is the expected value of the random component, is always going to equal 0. And we're also going to prove that the variance of x is going to be the same as the variance of u, that is sigma x, sigma squared x, is always going to equal sigma squared u. So in the next video, I'm going to prove these two